The Googol Year Timeline, How the Universe Will Die in Silence. A single photon slips free from the last black hole. No stars, no warm dust, just one final breath of light crossing a universe that can't notice. There's nothing left to scatter it, nowhere left for it to go. After this, only colder. To understand how a cosmos that once roared with fusion and fireworks ends in silence, we have to rewind to when everything was too bright to see. We'll walk the long slope from fire to quiet, from first atoms to final quanta, using the best physics we have. This isn't doom, it's a ledger. If our brief age has meaning, it's because we get to read it. Let's start at the first entries. Fire to structure, from plasma to first light. At the start, there isn't structure. There's expansion, fast then faster still. Inflation takes a seed of space-time and pulls it smooth, stretching quantum jitters into the faint fingerprints we'll one day call the cosmic web. When inflation ends, energy dumps into particles and radiation. The universe is a hot, opaque plasma. Photons trapped, charged particles jostling. No atoms, no light escaping. Seconds tick by. Protons and neutrons, born in that first torrent, begin to bind. Not everything sticks. The balance of forces and cooling rates decide the mixture. Mostly hydrogen nuclei, some helium, a trace of lithium. This quiet bookkeeping is nuclear archaeology that life will later depend on, even though nothing looks like life now. It's too dense, too bright, too busy. For hundreds of thousands of years, light can't travel freely. Photons bounce off electrons like pinballs, and every direction is the same glare. Then the temperature falls below a key threshold. Electrons settle into orbits around nuclei. Recombination, it's called, but really it's the first time atoms form. The fog lifts. Photons finally stream across space without being stopped. These are the microwaves we still see today, the cosmic microwave background, a baby picture taken when the universe was about 380,000 years old. But the picture isn't perfectly smooth. Tiny temperature ripples mark regions slightly denser or emptier than average. Gravity leans in. Over millions of years, those denser patches pull a little more matter, then a little more, building clouds inside clouds. The first structures begin as whispers, cooling gas pooling in dark matter halos that nobody can see but everything feels. In the darkness after recombination, there are no stars yet. Space is filled with neutral hydrogen, and the night is truly dark because nothing shines on its own. Then gravity crosses a threshold. Gas in the biggest halos compresses enough to ignite fusion. Population 3, stars, massive, short-lived, and metal-free, flare to life. They burn hot and fast, drowning their surroundings in ultraviolet light. Many die as supernovae, forging heavier elements and flinging them into space. With those elements, carbon, oxygen, iron, the chemistry of complexity becomes possible. Dust can form. Cooling becomes easier. The next generation of stars can be smaller, longer-lived, more varied. Meanwhile, something else is happening in the centers of those first galaxies. As gas collapses, some of it loses enough angular momentum to fall inward, deep inward. Dense stellar clusters merge. Black hole seeds appear. Maybe from direct gas collapse, maybe from the wreckage of the first giant stars. They start small, but in crowded, gas-rich galaxies. Small has a way of not staying small. Galaxies assemble by merging. Streams of stars and gas weave into disks and bulges, and each collision is messy and bright. Shockwaves trigger bursts of star formation. Supermassive black holes feed, launching jets that carve cavities in the hot gas. It's chaotic, but out of the chaos comes structure. Spiral arms, star clusters, planetary systems forming in dusty rings around young suns. Here's the stake that matters. Without those first heavy elements, there's no rocky ground to stand on, no water to pour, no biology to attempt anything. The universe is teaching itself to build, one supernova at a time. But even at peak creativity, there's a limit baked in. Fusion burns fuel. Gas supplies can be heated, blown out, or simply used up. The bright era carries its end inside it. While that's happening on grand scales, zoom in. In a newborn system, pebbles collide, stick, and grow into planetesimals. Gravity takes over, sculpting worlds that either melt into spheres or get smashed apart and tried again. The quiet of a stable orbit is hard won. 1,000 near misses decide which rocks become homes and which become rubble. By around 1 billion years, the night isn't empty anymore. Scattered across the sky, the first galaxies sparkle with clusters of young stars. The cosmic microwave background fades to a uniform whisper behind them. The universe has light sources now, but it's still learning to arrange them. Streams feed halos. Halos merge into larger halos. The cosmic web tightens. Its filaments. This was the moment everything changed. Once heavy elements exist, star formation doesn't just shine, it seeds. Each generation prepares the next. The path from plasma to planets is messy, but it's no accident. Gravity and cooling do the work, with feedback from explosions that both destroy and enable. Brightness peaks are still ahead. So is the long decline. For now, the lights are turning on. The Age of Starlight, peak formation to slow fade. Once the first metals seed the gas, the universe becomes efficient at making stars. Gravity funnels cold clouds into knots. Shocks and spiral waves compress them. Newborn clusters flare like neighborhoods switching on at dusk. The cosmic star formation rate climbs for billions of years, racing upward as galaxies collide and trade gas. Around 10 billion years ago, redshift of 0.2, it crests. That's the bright noon of the cosmos. Most of the stars you see in a deep field were born around then. After the peak, the curve starts to slide. Not a cliff, more like a long slope. Inside those lights, each star negotiates with time. Massive blue giants live fast and end violently, burning through their cores in a few million years and dying as supernovae that scatter metals and leave behind neutron stars or black holes. Sun-like stars sip fuel more carefully. They spend most of their lives steady on the main sequence, then bloat into red giants, shed their outer layers, and expose white-hot cores that cool into white dwarfs. Red dwarfs, the tiny majority, burn so slowly they'll outlast entire galaxies. Different clocks, same physics, fusion balances, gravity until it doesn't, and the structure changes. Planets form across this spectrum. Protoplanetary disks settle, dust grains grow, ice lines split chemistry into zones, rocky worlds huddle close. Gas giants congeal farther out where volatiles can survive. Metals matter. With more heavy elements, more solid building blocks circulate, and planet frequency rises. Habitable windows open and close as stars brighten, flare, and age. Some systems get long, quiet spans, others get slingshotted by neighbors or sterilized by a nearby supernova. Life has to thread narrow corridors through moving walls. Meanwhile, the expansion story drifts in a new direction. The universe isn't just getting bigger, it's accelerating. Dark energy, whatever drives it, pushes galaxies apart faster over time. Within a few billion years of the peak, this acceleration starts to isolate galactic neighborhoods. Gravity still binds local groups, but beyond that, distances can stretch so quickly that light sent toward us now from faraway clusters will never arrive. An event horizon effect for W for Bogus. The cosmic web looks connected, yet the threads are pulling taut. Inside galaxies, feedback starts to bite. Starbursts and active black holes heat gas and blow it out of disks. Halos keep some, lose some. The easy reservoirs deplete. What remains is often too hot to cool or trapped in tenuous streams that take eons to settle. The assembly line doesn't stop, but it slows. Future generations of stars become scarcer, and the average mass of new stars shifts lower. What was once a fireworks factory becomes a workshop with the lights turned down. Here's the sting for us. We live in the thin, bright slice. On a timeline measured in trillions, our age occupies a narrow ridge where galaxies dazzle, night skies teem, and heavy element chemistry is abundant. Our telescopes can still see the afterglow of recombination and the crowd of galaxies between us and the horizon. That won't always be true. Far future astronomers marooned in their local remnant will have fewer clues. But right now in the story, the universe is rich with extremes. Neutron stars collide in kilinovae, forging gold and platinum in R-process furnaces. Supernova remnants sweep the interstellar medium, compressing clouds and triggering new stars, even as they tear others apart. In galactic cores, supermassive black holes feed in messy episodes. Some launch narrow jets that stitch radio lobes across hundreds of thousands of light years, inflating bubbles in the surrounding plasma. These are the last true engines born of abundance. Nuclear at the stellar scale, gravitational at the galactic scale, each stealing free energy from the differences in density and temperature that still exist. As the star formation rate falls, the character of light changes. Blue light fades first because massive stars die young. Galaxies redden as long-lived, lower-mass stars dominate the glow. You can date a population by its color the way you can date a forest by its canopy. The universe is aging into a redder evening, and yet it's still busy on human scales.
Giant molecular clouds tumble and shear. Spiral arms keep marching. Open clusters drift apart like families after a reunion. In the halos, orphan stars carry scars from old mergers. The Milky Way itself is on a slow approach with Andromeda, a promise written in motion. But, for now, the overall tide is going out. Each generation leaves fewer raw materials for the next. This is the turn toward thrift. Gas is harder to gather. Heat is harder to lose. Distances are harder to cross. The universe keeps building, just at a lower budget. The torch is passing to the small and efficient. Red dwarfs, quiet, stingy, resilient, are about to inherit the future. The Red Dwarf Empire, trillions of quiet suns. Here's where the universe learns patience. After the blue giants fade and the bright factories slow, the sky shifts to a different rhythm. Red dwarfs, small, cool, stubborn, fill the scene. They're the most common stars by far, and they burn with a thriftiness that puts everything else to shame. A red dwarf attempted the sun's mass can sip its hydrogen for up to 10 trillion years. It's Washington the 13. That's 1,000 times the current age of the universe. If the Age of Starlight was a festival, this is the long, steady hum of the generators after the crowd walks home. These stars are simple in a way that helps them endure. Many are fully convective, meaning hot gas rises and cool gas sinks throughout the entire star. Fresh hydrogen from the outer layers cycles inward, and helium ash drifts outward. No dead core, no wasted fuel trapped in the center. They don't need to die young because they don't run out of accessible hydrogen in the core the way heavier stars do. They turn their whole bodies into light, slowly, like a candle that refuses to go out. Life near a red dwarf starts rough. Young red dwarfs can be loud, throwing flares and ultraviolet tantrums as their magnetic fields twist and snap. Planets close enough to be warm, because these stars are faint, you have to orbit tight, can get baked and stripped early. Many lock one face to the star, day forever on one side, night forever on the other. But as the star ages, it quiets. Flares grow rarer. Atmospheric chemistry settles. If a planet can hold on to air, winds can carry heat from day to night, tempering extremes. Habitability becomes a long negotiation rather than a brief window. Meanwhile, galaxies keep rearranging themselves slowly, invisibly, on spans that dwarf even geologic time. Orbits drift. Passing stars tug just a little. Over millions of orbits and countless near misses, systems reshuffle. Some planets are ejected, becoming rogues that wander between stars. Others migrate inward or outward, nudged by tides and weak resonances. In red dwarf neighborhoods, that slow dance continues with fewer big disruptions, because massive stars, the loud troublemakers, are gone. What's left is granular and personal. One dim star, a handful of worlds, a local story that can last longer than any previous chapter. Zoom out and the light changes color. Galaxies that once sparkled with blue now glow red and near infrared. The star formation rate remains above zero but inches downward. Each new generation is smaller on average, and red dwarfs are the default. The universe has chosen efficiency over spectacle. Energy budgets shrink, but they don't vanish. On planets that find a workable balance, winters can be measured in eons, springs in tens of millions of years. If there's biology, it adapts to dim skies and slow clocks, or it doesn't survive at all. While that was happening in the disks, the remnants multiplied. White dwarfs cooled, neutron stars spun down, black holes waited at the centers. Red dwarfs threaded between them like embers among ash, the only steady sources still adding fresh photons to the background. Their spectra are simple, their lifetimes generous, their habits predictable. That predictability is its own kind of drama. When everything else runs out, endurance becomes the story. There's a catch to endurance, though. Even the thriftiest spend. Fusion turns mass into light, and the mass leaves. A red dwarf brightens slowly over its life. Then, after trillions of years, it uses the last of its hydrogen. For the smallest ones, the transition is quiet. No red giant phase that swallows planets. No final blaze of glory. They dim into blue-white embers, proto-white dwarfs that shed their remaining heat on timescales that are themselves ridiculous. No such death has occurred yet. The universe, approximately 138 times 10 to nearest, isn't old enough to have seen one complete its life. We're extrapolating forward with physics that's been true everywhere else. Stellar migration continues its faint rearrangements. Globular clusters, if any still cling to their stars, erode grains of light into their halos. The Milky Way and Andromeda, on course to merge, will long since have made their giant elliptical descendant. Inside that quiet city of stars, red dwarfs will be the street lamps that never quite switch off. Encounters over unimaginable times scatter some, feed a few to black holes, and hurl others into the deep dark. But most just keep burning. Here's where the stakes bend toward philosophy. If consciousness ever learns to live modestly, if it can engineer patience, this is the
Era with time to spare. Trillions of years of stable power, small gradients, slow change. No easy metals raining from supernovae, no quick fixes. Resourcefulness isn't optional. Civilizations, if any, reach this far, would have to master storage, recycling, and heat management, knowing the lights will never be bright again. But the lights still fade. Fewer stars form. More red dwarfs cross the line from fusion to cooling. Each Ember that slips into the Degenerate class takes one more steady beacon out of the catalog. The universe doesn't go dark in a crash, it thins. Night by night on a cosmic clock, points vanish. Gravity remains, faithful and patient, tightening what little structure is left. And when even thrift can't pay the bill, the Red Dwarf Empire yields to a colder sovereignty, cinders, remnants, and the quiet pull that arranges them. The Degenerate era begins, white dwarfs and ember worlds. The Red Dwarf Empire fades into cinders, and the universe enters a quieter craft, cooling, settling, conserving. White dwarfs, expose stellar cores the size of Earth with the mass of a sun, take center stage. They aren't burning, they're glowing with leftover heat, supported not by fusion, but by electron degeneracy pressure, a quantum rule that says electrons won't share space. It's a hard stop on collapse, a pause between fireworks and oblivion. They shine like hot iron fading to black, radiating away the memory of starlight. These remnants form from stars up to about 8 times the mass of the sun. After the red giant shedding, what's left is mostly carbon and oxygen under crushing density. Nuclei packed so tightly that atoms lose their individuality. At first, some white dwarfs are so hot they fluoresce blue-white, lighting up planetary nebulae like brief lanterns. Then the shells disperse, the lanterns dim. Cooling begins in earnest, a process so slow it outruns patience. Trillions of years before many even cross into dull red. Quadrillions before they be invisible to almost everything. Black dwarfs, the final, fully cooled state, don't exist yet. The universe isn't old enough, but their future is written in the math. As white dwarfs radiate, their ions settle into crystalline lattices. Picture an entire star turning to a diamond-like solid from the center outward. That phase change releases latent heat, a last little grace that delays the dark. Observational hints of crystallization already exist in some cooling white dwarfs today. It's not dramatic. It's a whisper stretched across eons. Around them, planetary systems recompose themselves. With the star's mass reduced, orbits expand. The gentle gravity loosens grips, and stable arrangements wobble. Planets tug one another into new resonances. Asteroid belts go chaotic, feeding long, thin swarms of comets that skim past the Ember and bake slowly. Some worlds fall in, shedding angular momentum through tides, their crusts melted in quiet final acts as they spiral down. Others are kicked free, joining the growing population of rogue planets that drift through interstellar cold, warmed only by radioactivity and the faintest memory of internal heat. Brown dwarfs, failed stars too light to sustain hydrogen fusion, glow faintly in this era, a galaxy's worth of heavy Jupiter cousins radiating away the heat of their birth. They host their own little systems. Some will merge with other brown dwarfs or graze white dwarfs in long, improbable encounters, exchanging energy with tiny, persistent nudges. In a universe where nothing replenishes, these low-wattage sources are night lamps in abandoned rooms, comforting and insufficient. The interstellar medium changes character. No fresh supernovae seed it with easy metals. No giant stars stir it violently. Gas left in galactic halos is thin, hot, and stubborn to cool. Occasional collisions or accretion events flare briefly, but the baseline is quiet. Chemistry, once a roaring market of reactions driven by strong gradients, becomes a sparse trade. Complex molecules survive in cold-shadowed niches. New ones form slowly on dust grains, still orbiting embers. The rate of change falls so low that centuries blur into sameness, even for worlds that endure.
Here's the emotional weight. The memory of starlight is encoded in temperature. Every cooling white dwarf is a ledger entry, each photon a receipt for energy that once fought gravity and made structure. As the embers fade, that memory bleeds into space, stretched by expansion into longer and colder wavelengths. The background hum absorbs it all without comment, meaning, if it exists, has to ride on arrangements that can still do work, and those are dwindling. Meanwhile, gravity hasn't retired. It reorganizes the leftovers. In dense galactic cores, relaxation processes shuffle orbits. Three-body interactions nudge compact remnants into lost cones that point towards central black holes. Now and then, a white dwarf strays too close and is tidally shredded, releasing a short, hard flare.
That briefly breaks the long dusk. Elsewhere, binary white dwarfs lose energy to gravitational waves and merge. If the total mass stays below a limit, a heavier white dwarf forms. Above it, a type Ia supernova can still detonate, one of the last bright acts powered by degenerate matter. They'll be rare, but they'll happen like late fireworks in an empty park. Most white dwarfs avoid drama. They simply cool. Their surfaces turn red, then infrared, then radio cold. Their magnetism persists, sometimes siphoning material from passing debris, painting faint auroras across dead skies. Planets that manage to keep atmospheres find them freezing out, gases snowing onto ground in layers that mark deep time. Ice ages become the default. The only warmth is tidal friction, radiogenic decay, and the distant whisper of the core star's fading heat. It's a low-energy universe, but not a dead one. Processes that used to be washed out by brighter events now matter. Quantum tunneling in crystals, slow diffusion through dense cores, rare collisions in thin gas, all tick forward. Evolution, if anything lives, must track these clocks. Slowness becomes a habitat. Noise becomes scarcity, and scarcity becomes law. This is the threshold where memory starts to fail. Archives etched in rock erode atom by atom. Data in solids scrambles under cosmic rays and thermal noise across times that dwarf languages and species. If anyone wants a message to the future, they're already talking to a calendar made of erosion, and yet, the act of arranging still happens. Gravity keeps working even as chemistry stalls. The universe settles into patience. The embers dim. The ledger marches on. Galactic quiet, mergers, cannibalism, and isolation. While the embers cool, the big structures finish their slow negotiations. The Milky Way and Andromeda close the distance, pulled by a promise they can't break. Over a few billion years, tidal bridges stretch, halos interpenetrate, and star streams arc like pulled taffy across the night. The first pass is all torque and fireworks, but the gas supply is thin now. Starbursts happen just not like before. Friction with dark matter halos and countless close encounters drain the orbits. The spirals lose their definition. By the final coalescence, the pair is settled into one swollen elliptical, a red, round remnant with long memories and short tempers. We'll call it Milk Drumda, because someone will. In its core, two supermassive black holes find each other the way raindrops merge, first circling, then sinking, as passing stars steal their angular momentum. Dynamical friction does the slow work. When the holes finally bind, they radiate gravitational waves into the dark, a rippling payment to the fabric itself. The merger snaps them into one larger horizon, and the center grows heavier. The surrounding stars, what's left of them, reshuffle around a new gravity, while that hums in a register only space can carry. Cannibalism never stops. Dwarf galaxies that once orbited the Milky Way, then Andromeda, then their union, come in on stretched ellipses and dissolve. Each one leaves a ribbon of stars, low surface brightness braids looping the halo. Globular clusters sink gradually, tidally shredded into ghostly shells. The big remnant eats elegantly now. No messy tearing disks, just slow ingestion. The hot halo gas, shocked by mergers long past, sits at millions of degrees. It cools reluctantly. Without cold flows to feed it, the remnant star factory sputters. New stars still form, but it's a drizzle. Beyond this local feast, the stage is clearing. Dark energy keeps nudging the expansion. Over time, more distant galaxies slide past the line that matters, the cosmic event horizon. It isn't a wall you can point to. It's a limit on what light sent toward us now will ever arrive. As acceleration continues, most of the universe becomes permanently unreachable. From inside Milkdrumda, the sky outside the local group fades. Not because objects vanish, but because their light never gets a chance to close the gap. The observable shrinks to the personal. While the particle horizon grows, the event horizon limits future signals. Inside the remnant, time stretches out. Encounters between stars grow rarer as the population thins and the velocity dispersion rises. Even so, gravity is patient. Every close pass transfers a little energy. Over eons, some stars get kicks that lift them to wider orbits. Others are nudged inward, grazing the lost cone that points to the central black hole. A red dwarf that has burned for trillions of years can still meet an abrupt end. Spaghettified, its guts sprayed in arcs that light the core with a brief, hard flare. These are the rare fireworks of the quiet city, and they're getting rarer. Gas reservoirs tell the rest of the story. What remains in the halo is hot, tenuous, and stirred. It can cool, but only glacially. Without fresh infall from cosmic filaments, now effectively severed by expansion, the remnant recycles what it has. Dying stars shed material into a medium that's too warm to condense quickly. Feedback from the central black hole, even at low levels, keeps puffing the gas enough to postpone collapse. The thermostat is stuck low. The workshop lights flicker but don't go out. They just don't brighten again. Isolation changes what's knowable. Early astronomers used distant galaxies to measure expansion, map the microwave background to trace origins. Future observers, deep in the quiet, will see one galaxy, one background of their own making, a warm glow from stars and dust inside the remnant. The cosmic microwave background will be redshifted into wavelengths so long that local noise buries it. The evidence for a wider universe fades with the same steady grace as the stars themselves. It's not deception, it's a limit set by distance and time. Meanwhile, the dark economy continues. Three-body interactions in the core eject some stars entirely, flinging them into intergalactic space with escape velocities earned in tight dances around the black hole. Others spiral inward through 1,000 slight tugs. The center grows, not greedily, just inevitably. Stellar mass black holes drift down and merge into a heavier swarm, grain by grain. Neutron stars collide occasionally, but with the gas so thin, the afterglows are faint. The inventory shifts steadily from luminous to compact. If you could wait long enough, you'd watch Milkdrumda's profile soften further. Without spiral structure, there's no organized clock to count by, just a slow Maxwellian shuffle of stars finding statistical balance. The halo puffs out, the core tightens, the galaxy's color
deepens into the near-infrared as the last higher-mass dwarfs age off the main sequence. It isn't death, it's a long retirement. Here's the human angle folded into this enormity. Parochialism becomes physics. Each remnant is an island, and every island is alone forever. Local rules dominate understanding. If intelligence persists, it builds theories from within a closed system, inferring a past it can't see. Meaning, then, will be made in neighborhoods, not across the cosmic commons. The stakes aren't destruction, they're solitude, and yet the story has momentum. Mass keeps falling inward. The darkest hearts, central black holes, inherit authority. As the last drizzles of star formation dry up, the galaxy's energy budget is set by gravity and leftover heat. No new actors are entering. The cast is down to embers and wells. Everything is about to change when appetite meets emptiness. When there's nothing left to eat, even the kings of gravity will start to starve. The black hole Ascendancy, feeding in the dark. The remnant galaxy settles, but its center doesn't rest. The supermassive black hole sits in quiet authority, its event horizon a boundary where clocks bend and promises end. Around it, a sparse dribble of fuel still arrives. Old stars wander too close and lose a few layers. Disrupted gas clouds smear into thin accretion streams. It isn't the quasar age. No blinding beacons spanning millions of light years, just a low, persistent diet. Gravity, not fusion, writes the power bills now. Feeding in the dark looks different from the bright past. Without thick, cold gas, disks are lean, inefficient, and intermittent. A single disrupted star can launch a tidal disruption event, weeks to months of hard X-rays and ultraviolet, then a taper into silence. These flickers are rare but decisive, the last fireworks thrown by gravity's patience.
Every flare is an accounting entry. Mass in, radiation out, the horizon swelling by less than the total, because some energy escapes first. Bit by bit, the black hole grows. Dynamical friction keeps pushing heavy things inward. Stellar mass black holes born long ago from massive stars skim through the bulge, stealing momentum from surrounding objects. Each pass with a star or white dwarf trades energy. Over eons, the heavy settle toward the middle, forming a dark cusp. There, tight binaries harden through three-body encounters until gravitational waves take over, shrinking orbits and merging pairs into larger, deeper shadows. Space itself carries away the excess in ripples, a quiet chorus that never needed air. Unknown to them, across the remnant, ordinary stars are also clearing the board. Red dwarfs that survive trillions of years can still meet a sudden end. Stretched into spaghetti, heated, and smeared into a stream that circles, collides with itself, and glows before vanishing below the horizon. Encounters toss some clear of the galaxy. Others are gently herded toward the center, where lost cones, those narrow ranges of incoming trajectories, feed the black hole's appetite. Brief blaze, then nothing, like a match in wind. Meanwhile, the halo thins. Gas heated by old mergers and feedback cools at a pace that offends impatience but pleases infinity. When it finally condenses, much of it doesn't turn into new stars. It trickles inward, captured by the central potential. Even that is stingy. Low accretion rates mean radiatively inefficient flows, hot, thick, and dim compared to youthful quasar disks. Most of the gravitational energy tumbles across the horizon rather than escaping as light. The night grows poorer in photons and richer in mass. Here's the rule of this era. Engines survive if they can run on gravity. No fusion means no easy gradients, but deep wells can still do work by rearranging orbits. Star clusters sink, compact pairs merge, tidal tails deliver the occasional snack. It's a slow metabolism. A million years can pass between meals. On the black hole's timescale, that's fine. It doesn't age, it accumulates. What nobody knew at the time, because nobody lasts that long, is how thorough this quiet harvest becomes. Over enough encounters, most compact remnants either escape or get swallowed. The central hole increments upward, digit by digit, swallowing the ledger of its galaxy's past. It doesn't need to hurry. In a universe that's forgetting how to shine, being patient is the only talent that matters. Black holes away from the center participate too. Stellar mass holes in wide binaries swap partners during close passes, steal from white dwarfs, or drift until they meet fate in the core. Intermediate mass candidates, if they exist in old globulars, can grow by grazing captures, piecing themselves together out of many small meals. Each merger writes a gravitational wave signature, shrinking in frequency and growing in weight as the ladder climbs. And yet even this era has limits. After enough eons, the inventory of things that can be eaten thins to almost nothing, the remnant.
Becomes a museum of survivors, a scatter of red embers, a population of brown dwarfs, a halo of weakly bound debris, and a central well that's heavy but bored. The rate of tidal disruptions drops. Gravitational wave mergers become spaced by deserts of time. The last engines idle. Hawking temperature is still negligible. For black holes this massive, the effective temperature sits so close to absolute zero that the cosmic microwave background of earlier ages outshone it. But the background keeps redshifting. The bath cools. There's a crossing unimaginably far ahead when the universe is colder than even the black hole's feeble glow. For stellar mass holes after pain of 20 years. For supermassive holes far later. That's the signpost for a different story. Stakes sharpen here. If proton decay is real, matter thins on its own schedule and the pantry empties faster. If protons are stable, the pantry lingers, but the expansion and isolation still starve the process. Either way, the kings of gravity will outlast their kingdoms. They'll sit in the dark, waiting for food that doesn't arrive. When appetite meets emptiness, the only thing left to do is evaporate. The feeding stops. The whisper begins. Proton decay? The great maybe. We've been counting on gravity to carry the story forward. Now we hit a fork that doesn't care about galaxies at all. It's in the guts of matter. Protons, those sturdy building blocks in every nucleus, might not be forever. Some grand unified theories say they should decay, turning into lighter particles over mind-bending timescales. Experiments haven't seen it. The lower limit keeps moving. Protons, if they decay, live longer than about 10 to the power of 34 years. Current bounds vary by channel, many exceeding 10 to the 34, 10 to the 35. That's not a lifetime. It's a cliff hidden in fog. Why does this matter here? Because the future of everything solid hangs on it. If protons are mortal, then matter.
White dwarfs, iron cores, the quiet rubble of worlds will slowly disintegrate. Not explode, not crumble in one go, but bleed mass through rare, random decays that turn baryons into leptons and radiation. No chemistry can outweigh that. Over times up to 10 to the power of 36 years or even beyond, depending on the model, the roster of nuclei thins. Bound structures go from familiar to fragile to gone. If protons are immortal, then those structures persist much, much longer, and other slow processes decide their fate. In labs on Earth, tanks of ultra-pure water or liquid scintillators sit in the dark, waiting for a telltale flash. A proton in an oxygen nucleus turning into a positron and a pion, or some other allowed channel. Decades go by with nothing conclusive. For example, Superkamiokanda's limits push some modes beyond 10 to 34 years. The silence is data. It pushes the lifetime lower bound higher. But a bound isn't a proof. The theories that predict decay are tidy. They unify the forces at energies far beyond any collider. But nature isn't obligated to be tidy. Meanwhile, in the far future we're walking through, matter doesn't know what conclusion we reached. It just behaves. If protons do decay, a white dwarf's carbon and oxygen lattice becomes a slow fizz. Each rare event knocks out a piece, warms a spot, and the star adjusts, re-equilibrating as mass gradually evaporates into light and neutrinos. The star shrinks, then expands slightly as composition changes, but the main story is attrition. Planets feel it too. Rocks turn porous on atomic scales, then drift toward dust, then toward nothing recognizable. Neutron stars are trickier. Neutrons aren't free protons, but the quarks inside would also be subject to whatever the deep laws allow. Over a longer timetable, even those cores would unbind, their contents leaking into lighter particles that drift away into the cold. If protons don't decay, the ledger looks different. White dwarfs don't evaporate from within, they just keep cooling. Exotic proposals like iron stars, assembled by the slow gravitational settling and weak interactions in degenerate matter, could emerge over absurd spans. Fusion by quantum tunneling, a proton slipping through the barrier it doesn't have the energy to climb, might still happen in dense cold cores, a trickle that converts the last hydrogen into heavier elements on timelines that make trillions look like minutes. None of this is mainstream certainty, it's careful extrapolation. The core point stands. Stable protons let structure linger. Unstable protons force a fade. There's a human sting hidden in that fork. Memory is written in arrangements of matter. If protons decay, every archive has an expiration baked into the particles themselves. Not just weathering, not just cosmic rays, but the material erasing itself. If protons hold, archives still lose to diffusion, impacts, and freezing noise. But in principle, some arrangements could persist far longer, tucked into cold, protected niches. Either way, permanence is a story we tell on short clocks. Zoom back to our remnant.
Galaxy. The central black hole waits, the embers cool, the halo thins, proton decay, if real, accelerates the cleanup. Brown dwarfs turn ghostly. Rogue planets snow into faint spheres that then unmake themselves from the inside. The mass budget shifts from baryons to radiation and neutrinos that slip across expanses without caring about destinations. If protons don't decay, the cleanup is slower, but the ending isn't spared. Expansion and isolation still dilute interactions. Gravity still wins arguments about what can move heat around. The stage gets emptier. What nobody knew in the quasar age is how sharp this hinge would feel. A yes to decay gives the universe a chemical deadline. A no lets matter hold out, but not triumph. Cosmological chemistry ends either way because there's no free energy left to drive it. The difference is pacing, not verdict. That's why this chapter is a maybe that matters. And whichever branch we're on, the next act ignores the verdict. Black holes don't need baryons to tell time. They have their own clock ticking against the cold. The pantry will empty by decay or by starvation. Then the horizons, patient for eons, start to whisper. Hawking radiation, how giants fizzle. The pantry empties, and the kings are left alone with their horizons. That's when the whisper starts. Not from inside, nothing escapes from inside, but from the edge itself, where gravity makes time run strange and quantum fields refuse to stay quiet. Space isn't empty. It teems with fluctuations, pairs of particles that pop in and out like brief thoughts. Near an event horizon, that restlessness can become a transaction. One partner falls in with negative energy relative to infinity. The other escapes, carrying away a sliver of the whole's mass.
From far away, it looks like the black hole glows. This is Hawking radiation, a consequence of quantum fields in curved space-time. It isn't particles tunneling out of the interior. It's the horizon interacting with the vacuum's bookkeeping. The result is a temperature assigned to the black hole, tiny and precise. The smaller the hole, the hotter the glow. The larger, the colder. A stellar mass hole today has a temperature on the order of 10 to the power of -8 Kelvin. A supermassive hole at a galaxy's center is colder still, effectively at absolute zero compared to any ambient background the universe had for eons. So nothing happens, at first. As long as the surrounding radiation bath is warmer than the black hole, heat flows in, not out. For most of cosmic history, the cosmic microwave background was the louder voice, feeding the holes more energy than they could radiate. But expansion keeps stretching those background photons, cooling the bath. There's a crossing far ahead where the universe is colder than even the laziest horizon. Past that point, the sign flips. Every black hole, no matter how massive, is now losing. The timescales are almost rude. A solar mass black hole takes about 10 to the power of 67 years to evaporate, a number that makes galaxies and red dwarfs feel like mayflies. A supermassive one, 10 billion solar masses, runs its clock out near 10 to the power of 99, 10 to 100 years. The temperature rises as the mass falls, so the radiation starts unimaginably faint and slow, then accelerates. For most of its life, an evaporating hole is quieter than quiet. Near the end, it gets hot. The spectrum is thermal, like a black body, set by that tiny temperature. Early on, the radiation is mostly low-energy photons and neutrinos. As the mass shrinks, heavier species climb into reach, electrons and positrons, maybe even heavier particles, depending on what physics allows in that era. The horizon's glow brightens, still isotropic, still indifferent. If you could watch, you'd see the hole get lighter and hotter in a runaway feedback. Less mass makes higher temperature makes more radiation makes less mass. Meanwhile, there's the question that kept theorists awake. What happens to information?
If matter falls in arranged in some specific way, and the hole evaporates into a featureless thermal mist, do the details vanish from the universe? Quantum mechanics says evolution should be unitary. No data loss, just scrambled. For decades, this was the information paradox, a clash between gravity's horizons and quantum certainty. A lot of careful work points toward conservation winning, that the outgoing radiation isn't perfectly featureless, that correlations encode the history. Ideas like holography, where the horizon's surface area counts the enclosed information, give a language for this. It's not a settled derivation everyone agrees on in detail, but the mainstream view is that information isn't destroyed. It's just excruciatingly hard to read. Back in the timeline, the parade is orderly. Small black holes go first. Primordial holes, if any formed in the early universe, would have long since popped in flashes we might search for as brief gamma-ray bursts. Stellar mass holes wait unimaginably, longer than die-in finales that outshine their entire histories. Supermassive holes hold out nearly forever, each the last furnace of a marooned remnant galaxy. Their emissions are so cold for so long that the universe barely notices. Only at the very end do they matter as spectacle. Those final seconds are the loudest thing left. When a black hole gets down to mountain mass and less, its temperature climbs high enough to spew energetic photons, electron-positron pairs, maybe heavier hadrons if the energies allow. Power ramps like a siren no one hears. The last instant is a burst. Brief, intense, then gone. The horizon erased and the mass converted into radiation and light particles that race outward into a space with almost no gradients left to exploit. The stakes are tidy and merciless. Gravity's vault is emptying. All the mass black holes hid behind horizons is paid back into the universe as cold radiation over spans that make the word later meaningless. If proton decay erased the baryonic world earlier, Hawking radiation cleans up the rest. If protons didn't decay, this is still the end of engines. After the last black hole fizzles, the ledger is almost closed. What remains are low-energy photons, neutrinos, and a thin sprinkle of anything stable that escaped being eaten. The lights aren't just dim, they're functionally gone. And yet, the whisper matters. It's the universe enforcing its own accounting. No perfectly sealed vaults, no infinite storage, no exceptions to thermodynamics stretched by curved space. When the last horizon cools itself out of existence, the story loses its last power source. We're left with cold fields and stray quanta drifting through expansion, their wavelengths stretched, their interactions rare. The final transition is quiet, from hunger to heat loss, from gravity's authority to entropy's reign.
After the king's fizzle, only silence continues.
The Dark Era, photons, neutrinos, and lonely particles. After the last horizon hisses itself away, the universe doesn't go still, it thins. What remains are the quietest actors. Low-energy photons sliding toward longer wavelengths, neutrinos crossing everything as if it weren't there, and a sparse population of any stable particles that dodge collapse or decay. For example, electrons if permitted, possibly dark matter relics depending on its nature. No stars, no accretion disks, no furnaces, just fields and quanta tracing lines through growing emptiness. Activity doesn't stop, significance does. Entropy keeps climbing, not because something explodes, but because gradients vanish. Work needs differences, hot and cold, dense and thin, ordered and messy. The great machines that turned free energy into structure ran on those differences. Now, the temperature everywhere inches toward the same number, so close to absolute zero that saying it out loud feels like rounding to silence. Photons redshift under expansion, their wavelengths stretching like taffy until energy per quantum barely registers. They don't disappear, they get harmless. Neutrinos were always the ghosts. They scarcely notice matter even at their busiest. In this age, they become the default traffic, a background sea from the early universe, later topped up by every decay and evaporation we've already passed. They glide through the dark like gossip in an empty town, abundant, information poor, and not changing much. If anything interacts, it's by accident, a one-in-a-win event that takes longer than any calendar deserved. If protons decay, the baryonic world has mostly dissolved by now. The rubble of planets, the lattices of white dwarfs, even the dense oddities that survived earlier, all have leaked their rest mass into radiation and neutrinos, thinning the roster to light, lepton, and gravity's geometry. If protons are stable, pockets of matter remain, iron-rich clumps, dead quiet aggregates that barely interact except through gravity and the rarest of weak processes. Either way, chemistry is over. There's no free energy to jumpstart reactions, and the ambient bath is too dilute to push anything uphill. Meanwhile, every once in a great while, so rarely that once loses meaning, quantum tunneling plays its long game. A particle faces a barrier it shouldn't cross. Over absurd timescales, the wave function's tail finds a path. In dense, cold matter, tunneling could drive trickle fusions or transmutations that would have been swamped earlier. In vacuum, fields can rearrange through instantons, rare transitions that shave a sliver off some configuration and hand it to another. None of these events build structure. They're housekeeping on a floor nobody walks. There's a branch of speculation that threads through this era: iron stars. If protons don't decay, extremely dense, cold accumulations of iron could, over times that make Hawking clocks blush, fuse by tunneling into heavier nuclei, shedding energy as neutrinos and photons in a drip that mimics a slow doomed star. It's not consensus, it's an extrapolation sitting on multiple maybes. Nuclear physics at ultra-low temperatures, composition, and long-term stability. If it happens, it would be the final echo of fusion, not a revival. A candle in a cave, not a sunrise. Meanwhile, gravitational interactions still reorder the few survivors. Weakly bound objects drift farther apart as expansion stretches the fabric. Anything still in a bound halo stays bound, but encounters are scarce. Over stupendous spans, two-body relaxation and occasional three-body shuffles can still launch stragglers, feed a remnant compact object if one somehow survived, or drain the last tight binaries through gravitational radiation. But the rate is microscopic. You could wait 1 trillion times the age of the current universe and still call it quiet. The background light is a palimpsest of everything that ever happened. Starlight, once blue and bright, has redshifted into radio fog. Supernovae and kilonovae added their pages. Accretion disks wrote in X-rays, jets wrote in gamma. Hawking radiation from evaporated holes blended in the endnotes. Now all of it is stretched thin, smoothed by expansion, assembled into a cold bath whose only drama is that it keeps chilling. The cosmic microwave background, that original baby picture, has long moved into wavelengths so enormous they're better described as moods than colors. From a human angle, this is the part of the story that resists empathy. Nothing here cares about seconds, years, or civilizations. Memory fails because the media that held it, rock, ice, data stored in any substrate, suffers slow diffusion and quantum noise that eventually scrambles bits. With no active maintenance and no way to pump heat away efficiently, even the best vaults leak order. Archives become patterns, patterns become dust. Dust becomes a count of particles with no arrangement that matters, and yet the universe hasn't contradicted itself. It's following the same rules that made the Bright Ages possible. The arrow of time, set by entropy moving toward its maximum, points the same way it always did.
What changed is supply. Free energy fueled structure. Structure paid it back as waste heat. The ledger balanced. In this era, the balance sheet approaches its last line items. Small credits and debits written by tunneling, the rare capture, the occasional decay. They don't add up to a project. They're leftover coins. The feeling of an ending can be misleading. No wall, no curtain, no final chime. Just a limit. With no gradients left, no engines run. With no engines, no chemistry, biology, or thought can sustain itself. Activity remains, sparse as stars in a voided sky, but nothing organizes it into stories. That's the cost of a universe that used its differences well. The Dark Era isn't punishment, it's the receipt. And still, there's one card left in the deck that could flip the table, the vacuum itself. Vacuum mysteries, false vacuum, and metastability. There's one piece we've tiptoed around that could erase the whole board without fanfare, the vacuum itself. Not the absence of stuff, but the energy of empty space. The fields that still have values when everything else is gone. In our best-tested physics, the Higgs field gives particles mass by settling to a non-zero value. It sits in a valley of potential energy. The question that keeps theorists cautious is whether we're in the deepest valley, the true vacuum, or just a local dip, a false vacuum that only looks stable because the walls are high and we haven't tunneled through. Standard model calculations, using measured Higgs and top quark masses, place us near a boundary. The numbers hint the electroweak vacuum might be metastable, long-lived but not guaranteed eternal. There are uncertainties, especially in the top mass and higher order effects, that blur the verdict. The safe bet is that if it's metastable, the lifetime is stupendously longer than any timescale we've named so far, far beyond black hole evaporation. But metastable doesn't mean forever. It means not yet. If a transition happens, it wouldn't start with a bang you could see coming. A quantum fluctuation at some point in space could nucleate a true vacuum bubble, a tiny region where the fields tip into a lower energy configuration. If that bubble beats surface tension, it becomes favorable to grow. Then it expands at a speed so close to light that warning is a meaningless word. The bubble wall sweeps forward, rewiring physics as it goes. The constants that set chemistry and particle masses could change. Electrons might be heavy or massless. Protons might be unstable or bound differently. Inside the bubble, familiar structures disintegrate into whatever the new rules allow. There's no pain, no time to react, and no privileged frame to spot the front arriving. One instant you exist. The next, you're part of a different story. It sounds like a disaster movie. It's actually colder than that. There's no shockwave you can outrun, no shelter that helps. And crucially, the odds, given current estimates, are remote beyond comfort. If the vacuum is metastable, the decay rate per volume is so tiny that even integrated over an expanding universe and absurd spans, the expected waiting time is astronomical to the point of parity. We're not playing with a hair trigger. We're noting a theoretical possibility the equations allow. What nobody knew in the Bright Ages is how this risk threads the rest of the timeline. It doesn't depend on star formation, on black holes, or on the fate of protons. It rides on the shape of a potential we measure indirectly. The same framework that gave us the Higgs and predicted its interactions leaves a sliver of parameter space where a deeper valley exists. Small shifts in inputs move us between stable, metastable, and unstable. Our measurements put us in the middle category with a lot of caveats. That's why people talk about it with care. There's a common worry tied to human experiments. Could particle colliders trigger such a collapse? The short answer is no. High-energy cosmic rays crash into Earth's atmosphere and into other planets, stars, and interstellar gas, with energies far beyond anything human machines reach, and they've been doing it for billions of years across a vastly larger target. If such collisions could nucleate a bubble, the universe would have had ample chance to do it already. Safety studies addressed this specifically and concluded we're not uniquely dangerous. Nature has been running higher stakes tests at scale for eons. Meanwhile, the accelerated expansion plays a quiet role. If a bubble forms, it grows at near light speed relative to local space. Expansion stretches distances, but can't outrun a front moving through the fabric. In practical terms, if it starts anywhere in our future light cone, it arrives without forewarning. If it starts outside, we never know.
There's no partial update, no horizon glow. Either we learn by being rewritten, or we never learn at all. So why include this chapter at all given the odds? Because it's honest about our ignorance, and because it frames heat death correctly. The slow fade we've been tracing assumes the vacuum holds. If it does, the universe drifts toward maximum entropy. Cold, thin, forgetful. If it doesn't, the end isn't heat death. It's replacement. Not fire, not noise, just a silent swap of rulebooks that annihilates the meaning of structure we've been using. Both outcomes are consistent with what we know. One is sedate, one is absolute. Here's the strange comfort. We don't need to pick the likely lifetime of metastability swamps every other clock. Black holes evaporate first. Proton debates resolve long before vacuum risk comes due. On human scales, even on planetary or galactic scales, the vacuum is steady enough to build civilizations, write histories, and argue about endings. We act inside a stability that's either true or long-lived enough to matter. If the vacuum holds, the dark era keeps thinning. If it flips, there's no epilogue, only new physics everywhere at once. Either way, our quiet ledger turns its next page. Big Rip, Heat Death, Big Crunch, framing the fates. We've sketched a universe that fades, not explodes. But before we let the clock run out, we have to ask what the expansion itself plans to do. The driver is dark energy, whatever's causing space to stretch faster over time. Its behavior is summarized by one number, W, the ratio of pressure to energy density. If W equals -1, dark energy acts like a cosmological constant, steady, unchanging, a uniform push. That's our best reading of the data today. If W drifts above or below, the end can look different. Start with the default W approximately -1. In this scenario, dark energy's density stays constant even as space grows. Matter thins, radiation redshifts, but the vacuum's push keeps the Hubble expansion from slowing much. Structures already bound, galaxies, clusters within their local wells, stay bound. Everything else recedes beyond communication. Temperature slides towards zero as free energy runs out. No catastrophe, just attrition. This is heat death. The name sounds dramatic, but it's really a description of maximum entropy, where gradients vanish and no engine finds a foothold. Meanwhile, there's a more reckless branch. W less than -1, sometimes called phantom energy. If the energy density increases with expansion, the push strengthens over time. Gravity doesn't just lose on large scales, it gets unbound locally. In the Big Rip picture, timing matters. Far in the future, clusters tear apart. Later, galaxies. Closer to the end, solar systems unglue. In the final moments, atoms themselves lose their grip, the space between particles dragged wider by a runaway expansion. Observations make this outcome unlikely. Constraints keep W very near -1, but they don't slam the door. It's a tail risk with a clear, brutal narrative. Then there's the nostalgic option, a big crunch. That would require the expansion to slow, stop, and reverse, bringing everything back together. In a universe dominated by matter, this was once plausible. With dark energy pushing outward, and with measurements showing flat or near-flat geometry and acceleration, a global recollapse looks ruled out for any constant W near -1. You'd need dark energy to switch off, or flip sign, or some new physics to emerge that turns the tide. It's not impossible in the space of all theories, it's just out of step with the data we've collected. What nobody knew in the Bright Ages is how precise these measurements could get. Supernovae as standard candles showed the acceleration first. The cosmic microwave background pinned geometry and matter content. Baryon acoustic oscillations traced expansion over time. Put together, they sketch a consistent picture. Cosmological constant fits. Drifts in W, if they exist, are small within current errors. That makes heat death the sober forecast, with quantified, shrinking uncertainties. If we keep it human, our branch of the story doesn't change much under any of these. Big Rip would truncate the long quiet with a dramatic finish. Yes, but on timescales that treat the age of galaxies like a footnote. Big Crunch requires a reversal we don't see signs of. Heat death keeps the timeline we've been following, a succession of dwindling engines until black holes evaporate and fields relax into cold. There's another subtlety. Even in heat death, maximum entropy isn't a single magic moment. It's an asymptote the universe approaches. As expansion continues, the maximum possible entropy grows because there's more space to fill with low-grade radiation, more horizon area for everything to smear across. The universe chases a moving target and never quite catches it, always sliding closer, never arriving. That's why the end feels like a limit, not a curtain. Dark energy's constancy also sets horizons that matter for observers. With W equals -1, each island universe is bounded by an event horizon, a limit to what can be seen or influenced. That horizon carries an entropy proportional to its area, a bookkeeping that echoes black hole thermodynamics. It's another way the cosmos enforces quiet. Even if you had perfect patience, there's a ceiling on the information you can gather from beyond your patch. The big shared conversation ends. Local talk remains. If, against current odds, W dipped below -1 and stayed there, the big rip would rewrite those horizons on a schedule. Bound systems would face deadlines. The math assigns dates. Clusters unbind millions of years before the end. Galaxies later. Planetary orbits closer still. Molecules in the final heartbeat. It's clinical and unnerving. But again, measurements push W close to -1, with no convincing evidence that it's crossing into phantom territory. Confidence matters here. Scientists don't just pick a favorite ending. They weigh models against data, then attach error bars. The consensus today, cosmological constant, heat death, comes with a known margin. Future surveys, better standard candles, gravitational lensing maps, and improved cosmic microwave background measurements will tighten the bounds on W and its possible evolution. Maybe the error bars shrink around -1. Maybe they drift slightly. Either way, the roadmap becomes clearer. So we file the fates properly labeled. Big crunch, aesthetically tidy, observationally disfavored. Big rip, cinematic, constrained but not eliminated. Heat death with a cosmological constant. Boring, relentless, and supported. That's the frame. No trumpets, no apocalypse, just physics choosing the quiet path. Because the parameter happens to sit near -1. And with those candidates aired, the narrative returns to the long fade we've been tracing. It's not resignation, it's honesty about the slope we're on. The vacuum holds. The islands isolate. Engines spend the last of their budgets. Entropy writes its slow, legible script. We go back to the quiet timeline and let it run to the end. Timescales that break intuition. Map of the far future. To feel what comes next, we need a ladder of time. Start at a heartbeat, 1 second. Stack them into minutes, hours, years. A human life, a few billion seconds. Civilization, 10,000 years, 300 billion seconds. Now we jump. The age of Earth, 4.5 billion years. The Milky Way's disk orbits in a couple 100 million. Already we're past experience. And yet, this is nothing. Climb again, 10 billion years. The cosmic noon we described, already in the rearview mirror. 100 billion. Most galaxies outside the local group slip beyond our reach. 1 trillion years. Red dwarfs rule the skies, patient and dim, with new star formation limping. 10 trillion. Many of those dwarfs still steady. The bright era is a rumor. 1 quadrillion, the first of the smallest red dwarfs start retiring into white dwarf embers. These numbers aren't decoration, they're the cadence of the remaining plot. Milestones anchor the map. The last truly new star, formed from cooling gas that somehow found a way to condense, flickers on somewhere between trillions and tens of trillions of years. The last supernova, likely from a delayed white dwarf detonation in a binary, fires much later, a final sharp spark in a dark field. White dwarfs keep cooling, their crystals growing, their light shifting past red into radio and beyond. Black dwarfs, the fully cooled corpses, won't exist until roughly 10 to the power of 15 years or later, depending on mass and composition. We've never seen one. The cosmos is too young. If proton decay is real, another clock ticks behind the scenery. Around 10 to the power of 34 to 10 to the power of 36 years, ordinary matter begins to thin from within. That process doesn't stop the gravitational rearrangements, but it edits the cast list, dissolving the solids that held long memories. If protons are stable, strange possibilities, like tunneling-driven fusions and dense remnants, stretch the activity, but only as a trickle. Either way, the big engines are quiet. The clean, universal clock belongs to black holes. The last stellar mass black holes evaporate somewhere near 10 to the power of 67 years. It's an absurd number that still counts as early compared with the giants. Supermassive black holes, the ones that anchor remnant galaxies, outlast everything. 100 quintillion years, a Googol, 10 to the power 100, and change, saw them radiate away their horizons in whispers, then brief shrieks. After that, the universe's inventory narrows to light, neutrinos, and any stubborn relics allowed by fundamental physics. This is where entropy's ledger matters. Complexity peaked early because free energy peaked early. The steepest gradients, the biggest drops from hot to cold, dense to sparse, existed when star formation was common and gas could cool fast. Structures, stars, planets, biospheres, cities, are machines that ride those gradients, turning them into local order. As the gradients flatten, the ability to build and maintain complexity fades. The universe doesn't forget how to make patterns. It runs out of what patterns feed on. Memory follows the same slope. Records are arrangements that resist noise. On short scales, we beat noise by active maintenance, recopying, shielding, error correcting. On cosmic scales, maintenance is a luxury that fails. Radiation flips bits, diffusion smooths edges, thermal noise jitters atomic positions, impacts and tides erase surfaces. Over millions of years, this is geology. Over trillions, it's a solvent. Push to 10 to the power of 30, 10 to the power of 40, and the question stops being what medium works and becomes what medium still exists. In a universe that's cooling and expanding, copies become ghosts, then statistics, then background. Here's the part that betrays intuition. Time dilates emotionally as it stretches physically. In a human story, a century carries weight. In a cosmic story, a century is the thickness of a line. Trillions of years will pass with fewer headline events than fit in a single astronomical catalog today. The important thing isn't the count, it's the scale. Once stars dim and black holes take over, waiting detaches from meaning. Engines that need differences go idle. Processes governed by tunneling and evaporation whisper across durations that bury language. So we draw a map in simple marks. Bright age, 0 to tens of billions of years. Galaxies, stars, chemistry, life possible in many pockets. Red dwarf age, trillions to quadrillions, dim, stable, thrifty. Degenerate age up to 10 to the power of 15 and beyond. Embers cooling, collisions rare, archives failing. Black hole age 10 to the power of 40 to 10 to 100 plus, gravity's vaults evaporating in the cold. Dark era, after fields, photons, neutrinos, and the last stubborn particles drifting in near equilibrium. Along the way, open questions attach dates, but don't change the contour. Proton decay shifts when solids dissolve. Vacuum metastability threatens a rewrite that ignores the schedule, but the best estimates put its odds so low and weights so high that the black hole calendar still runs. Big Rip needs a different value of W than we see. Big Crunch needs a reversal we don't measure. Confidence isn't arrogance, it's a claim to be updated by data. For now, the quiet path stands. We're left with a map that's honest about scale. You can climb it with exponents, but you can't feel it with memory. The future isn't a cliff, it's a desert. Wide and flat, where a few thin rivers run for unfathomable distances before soaking back into sand. The meaning, if we want any, isn't that nothing happens. It's that what matters happens early, when clocks still find purchase, and that the tail, long, cold, and patient, is the natural end of using differences well. The last flickers, quantum tails, and final decays. We're past engines, past horizons, past anything you could call weather. What's left are tails, the thin, stubborn probabilities that never quite hit zero. They don't build new stories. They tie off old ones with knots you almost can't see. This is where time turns from a road into a horizon, and where physics, still precise, speaks in the quietest register it has. If protons decay, that long verdict has basically cleared the stage by now. Any remaining baryonic matter has bled into leptons and radiation over spans that stretch to 10 to the power of 36 years and beyond, dissolving any last intricate arrangements into simpler pieces. If protons don't decay, the rubble persists, but only as cold, dense clumps with nothing left to do. Either way, the last power source with a schedule was hawking radiation, and we watched it pay out. Now the universe is a ledger almost closed, with only quantum rounding errors left to sum. Those rounding errors still work. Quantum tunneling is the headline, an electron or nucleus facing a barrier it shouldn't cross, finding a path anyway because waves aren't edges. In dense, cold matter, tunneling fusion could trickle along at a rate that makes memory look instant. One reaction per chunk over times that make 10 to the power of 100 years feel like a weekend. If protons are stable, some models let iron-rich, ultra-dense clumps creep toward heavier nuclei via tunneling, slowing energy as neutrinos and faint photons. It doesn't reignite anything. It's erosion, not growth. Meanwhile, everything thermal is dragged thinner by expansion. Photons, already cold, keep redshifting. Neutrinos, barely social to begin with, drift as the baseline population. Gravitationally bound pockets, if any survived, are quiet to the point of parity. Sometimes, in absurdly rare coincidences, two relic particles scatter with a whisper of energy exchange.
Sometimes, a metastable bound state rearranges, spitting out a low-energy quantum that adds almost nothing to the bath. These are events, not episodes. There is one piece of deep time that can sound like resurrection if you frame it wrong. Poincare recurrences. In a finite system with fixed energy, classical mechanics allows it to wander arbitrarily close to a previous microstate, given enough time. Quantum mechanics has analogs, but the numbers are savage. Timescales double exponential in entropy. For any region with an event horizon, horizon entropy dominates, and the recurrence times are like 10 to the power of n, with n itself huge. They're not calendars. They're proofs that almost never can still be not never. They won't rebuild a city. They barely rebuild a fluctuation that looks like a puff of order before the bath dissolves it again. In de Sitter space, such fluctuations are framed as Boltzmann fluctuations and are similarly inconsequential to sustained complexity. Micro-black holes might, in principle, flicker into existence as rare fluctuations in a de Sitter-like spacetime with a horizon temperature, then evaporate with quick flashes. They'd be the briefest candles in the deepest cave. Quantum borrowing paid back with interest in a tick. If the vacuum is exactly a cosmological constant, that horizon temperature stays, and such fluctuations are part of the long tail. If dark energy drifts off, even that stage whisper fades. Either way, no gradient lasts long enough to power anything complex. Physics grants a receipt, not a revival. The longer you sit with it, the more the word silence turns literal. Not an absence of sound. You lost mediums ages ago, but the end of differences that could be listened to. No more hot versus cold worth harnessing. No more dense versus diffuse to coax into engines. Entropy doesn't hit a ceiling. It stretches toward an ever-retreating maximum as space expands, and the universe keeps walking toward it on feet made of probabilities. From our vantage, the emotional turn is clean and hard. We told a story because gradients allowed chapters. Stars lit one set. Black holes wrote another. Now the narrative thins into statistics. You can still list events. A tunneling here, a fluctuation there, a micro-black hole flicker, a decoherent shuffle that lands briefly on a pattern and then slides off. The listings aren't lives. The cosmos runs out of ways to say "and then" without lying. If protons were mortal, nothing composite survives to hold a shape. If protons hold forever, the shapes that remain have no budgets to move heat around. In both branches, the difference is cadence, not outcome. The last flickers aren't lights you can see. They're the edges of possibility, still technically open, practically closed. The silence isn't sudden. It's the limit of what can happen. Approached from below, never crossed, needing no curtain to end the play. Human angle, how to live before the lights go out. We sit in the loud part of the timeline, the brief window when differences are generous and engines easy. That's luck on a cosmic
scale. The universe won't promise permanence, so the question shifts. What's worth doing when the clocks don't care? Start small and honest, meaning isn't mined from eternity. It's made locally, between people, in places, across projects that might fail and still be worth it. We don't need forever to build value. We need gradients we can reach. Curiosity into understanding, fear into care, raw resources into culture. On this planet, for a blink, those gradients are abundant. That doesn't excuse recklessness. Entropy awareness isn't doom, it's a design brief. Systems break, maintenance matters. Civilizations last longer when they budget for repair, redundancy, and recovery. You stabilize climate because chaos eats futures. You guard biospheres because they're the rarest machines for turning sunlight into stories. You treat information as fragile because the universe is already eroding it, one random flip at a time. Humility helps. That perspective shrinks ego but expands duty. We aren't the point of the cosmos, we're a product of it. If intelligence is a way the universe notices itself, then stewardship is self-respect. Clean energy, resilient infrastructure, planetary defense, patient science, none of that changes the heat death ledger. It changes the chapters we get to write before the ink runs thin. Awe isn't escapism, it's fuel. Standing under a sky full of star formation you can't see and black holes you'll never visit can make the next good decision feel obvious. Take care, learn more, leave fewer messes. The timescales ahead dwarf us, but the present still multiplies. Each experiment that tightens W, each neutrino detected, each map of a dying galaxy made, pays into a common account of understanding that outlasts individuals, if not the universe. That's a worthy game with known rules. There's also a hard kindness in accepting limits. Projects framed as forever
collapse under their own marketing. Projects framed as long enough to matter stand a chance. Archive like a gardener, not a pharaoh. Many copies, various mediums, active tending, honest expectations. Teach so knowledge survives people, not just platforms. Build institutions that can admit mistakes without breaking, because entropy attacks brittle things first. We're not alone unless we choose to be. Even if the cosmic commons thins into islands, we live in the thickest confluence known. One world, one star, one species, capable of planning beyond a season. The best hedge against cosmic silence is collaboration now. Shared standards, open data, science done in daylight. If someone else is out there, they're writing the same physics, making the same bargains, maybe we never meet. Maybe we leave signs anyway. Not because they'll be read, but because leaving them is part of living well. Here's the quieter part. Joy counts. Music, jokes, tenderness, craft. None of it alters expansion. All of it converts free energy into arranged moments that make being here mean something. The arrow of time gives us one-way tickets. It also gives us cadence. We build rhythms inside an irreversible flow. That's not a flaw. That's the condition for stories at all. So we return to the last photon with clearer eyes. It isn't a threat. It's a reminder that everything we do costs energy and that spending well is the only metric that lasts. We're not saving the universe. We're learning to be decent tenants in it while the lights are still on. That's enough. That last photon is the receipt. Every flare, thought, and failure balanced against the universe's patient accounting. Before we go, here's the human stake. We live in the only loud window the cosmos offers. Use it well. If you want the prequel, the messy birth that set up this quiet ending, watch the origin story next. Subscribe for more true, unsettling science, where the stakes are real, the clocks run one way, and our brief brightness still matters.